Hi, this is Thomas. I'm going to teach you about the differences between an arithmetic function and a geometric function. So an arithmetic function, I'm sorry, I said functions, I meant to say sequence. An arithmetic sequence is a sequence where there is a constant difference. For example, you would have 2, 4, 6. As you can tell, there's a constant difference. So we go 6 minus 4 equals 2. 4 minus 2 equals 2. So there's always that constant difference. For a geometric sequence, you'll notice that there's a ratio of there's a process of it being multiplied by each other. So for example, we have 2, 4, 8, 16, and it goes on. So we would notice that the ratio being something like that, 4 divided by 2 equals 2, 8 divided by 4 equals 2. So as you can see, the ratio, it has a constant ratio of 2, whereas an arithmetic sequence has a constant difference of 2 in these two examples. Okay, so next objective under Unit 4 is finding the nth term in arithmetic and geometric sequences. So for an arithmetic sequence, what we do is we find the difference, then we have our n, d stands for difference, and then what we do is we add the first number minus, so the first number, and we're going to subtract that by the difference of whatever the difference is going to be. So say for example we have let's see, $17, $25, $33, $41, goes on to $1,121. So as you can see, 25 minus 17, that gives us 8. 33 minus 25 also gives us 8. So our difference is 8. So we have 8n being right next to n plus, so our first number being 17 minus 8, which is our difference, which gives us 8n plus kind of a funky looking 9, but nevertheless, I'll just go ahead and erase it. 8n plus 9. So that's for an arithmetic sequence. Geometric sequence is what we do is we take the first term and we're going to multiply it by the ratio. So for example, we have the sequence 2, 4, 8, 16, 32, 7, 6, 8. So what we're going to do is we're going to multiply 2. Our ratio is 4 divided by 2, so we got 2. 8 divided by 4 also gives us 2, so our rate is 2. 2 raised to the n, and minus 1 because we figure for the number that's being overcounted. So that's why we minus the 1. So that is how you find the nth term in arithmetic and geometric sequences. Okay, I'm going to go over how to find the number of terms in a geometric and arithmetic sequence. For an arithmetic sequence, all you do is take the last term minus the first term, and then you add 1. So, say for example, we have sequence 17, 25, 33, 41, so on and so forth, till we get 1,121. So what we do is 1,121 minus 17. So that will give us 401. So 1,104 plus 1 equals 5. All right. So for a geometric sequence, what we do is we take the first term, multiply it by the common ratio, indicate that as r, and raise that n minus 1 equal to the last term. So we have an example of a sequence 2, negative 10, 50, negative 250, so on and so forth, to big number, negative 9, 7, 6, 5, 6, 2, 5, 0. Okay. First term being 2 r n minus 1 equals negative 9, 7, 6, 5, 6, 2, 5, 0. So we want to solve for n. We'll divide both sides by 2. Calculator, come in handy. 56250 divided by 2 gives us 488282125. So we'll take the log of both sides. So our rate that we're moving up by, so we're by negative 10. So our rate is negative 5. So negative 5 raised to the n minus 1. Now, you can't take a log of a negative number, so we're just going to go with the log 5. Take log 5, and the log of 48281,250. So I have it on my calculator here to be able to make that easier. So take the log of that divided by the log of this divided by the log of 5, so we can isolate n minus 1. And that gives us 11. So n minus 1 equals 11. We'll add 1. So that gives us 12 as far as the number of terms in this specific geometric sequence. And yeah, that's it for finding terms in arithmetic geometric sequences. Okay, so this objective number 4, and under unit 4, I'm going to be going over the sum of a given sequence. So this is also a correction on finding the number of terms in an arithmetic sequence. So what I'll do is I'll take the last term minus the first term divided by the difference and then add 1. What I did last time is I didn't divide by the difference, which is a key part of that. So 25 minus 17 is 8, 33 minus 25 is 8. So we know that our difference is 8. So last term being 1,121 minus 17. So 1,121 minus 17. Whoop. Equals 1,104 divided by 8. 138 plus 1 equals 139. Okay, now with this number of terms, we're going to divide that by 2, essentially making into pairs. We're going to multiply that by the sum of the first term and the last term, 1,121. So 1,121 plus 17 equals 1,138. Now 139 divided by 2 gives us 69.5. Now we're going to multiply that by 1,139, and that will give us 79,091 as far as the sum of this given sequence. So I'll go ahead and erase that and make room for the geometric sequence that I'm about to do here. So with a geometric sequence, to find the sum of the terms, we take the last term, so 32,768. We're going to multiply that by the rate. So we figured out 4 over 2 is 2, 8 over 4 equals 2, so our rate is 2. And then, once we have that, we're going to subtract the first unit, so we're going to subtract that by 2. All of this will be divided by the rate, so we're 2 minus 1. Okay, so 32,768 times 2 gives us 65,536 minus 2, 65,534. 534. Okay, and we're going to divide that by 1, which leaves us with 65,534 as a sum of this geometric sequence. Now, when it comes to converging on an infinite geometric sequence, so we'll have, let's say, one piece of paper, and divide that in half. We divide that in half, that in half. So we essentially have 1/2, 1/4, 1/8, whoops, 1/8, 1/16, and 1/32. Now, this will continue to divide forever and ever and ever and ever and ever and ever. But it is finite because all of these fractions will eventually add up to one piece of paper. So that's how you can determine, you can look at an infinite number of sequences. Now there is an equation, given how you can find this, you're like, well, what's it eventually going to amount to? So the equation is as thus. What you do is you have the first term divided by 1 minus the rate. So before we had 1/2, 1/4, 1/8. So first term being 1/2 minus the rate, which is essentially 1/2. So minus 1/2, which leaves us with 1/2 divided by 1/2. So 1/2 divided by 1/2 is the same as 1/2 times 2. 2's cancel out, and voila, we have 1, which was the same number that we had as that piece of paper. So that's what you do with an infinite sequence. Okay, objective number 5 under Unit 4 is writing arithmetic and geometric sequences in sigma notation. So I'll start out with arithmetic. So our sigma notation is thus. Now, we'll have this number, n, is the number that we'll begin with. So we'll start, it means we're starting at 17. So 1 represents 17, or well, whichever term it is within the sequence. Now the number to the right of the sigma notation is the nth term. So in this case, it's it's what we found out before. It's plus 8, so it's 8n plus 9. All right, and now the number of terms is what goes on top. So back to what we were talking about. The last minus the first divided by the difference plus 1. So 21 minus 17, 1104 divided by 8 plus 1 is 139. So that's how a sigma notation would look like for this specific sequence that's arithmetic. Now, for geometric, it's basically the same thing. So in this case, we have 2n times 2. We'll start on number 1. Now, our number of terms in this sequence that we found before can be found as the last 32,768 times the rate. So it's by 2, this being the rate, minus the first, divided by the rate minus 1. So that's eventually going to be 1. So disregard everything that I just said. What I just did, I made a mistake. That was actually the sum of the terms, not the number of terms. So arithmetic, I did do that correctly. This is the number of terms. Now, the number of terms for geometric is the first term, so that'd be 2 times the rate raised to the n minus 1, which is the same as that and that. So equals 32,768. All right, 32,768 divided by 2. Leaves this with 2 and minus 1 equals 16,384. Now we're going to take the log of both sides. So we're running out of room here. But log 16,384 divided by the log of 2 leaves me with 14. 14 plus 1, because we still have n minus 1 equals 14. Add 1, so n equals 15. So our number of terms for this one is 15. So that is how sigma notation will look for arithmetic and geometric sequences. Okay, so objective number 6 is using sequences as part of real life applications. And so, one of the things that we talked about was a man's bungee cord that was 200 feet long, and the rebound of it was about 60% of it would rebound 60% of the length each time that it dropped. So, going down more and more each time. So this would be represented as something times n. So, and it would be a geometric sequence because it's not a constant first difference. So what you could even do is do the sigma notation. You have your initial amount, and so it's a sequence that just keeps going down and down and down. So it would be although it would be a negative, and then I figure out the number of terms there. It's difficult to describe or to do a real life application without actually having real data. Yet we have done it in class, and it is possible. And so I'd like to imagine a guy, woohoo, I'm about ready to bungee jump. And so it would 200 feet, and then the 60%. So there is real life application to this, and this is my Unit 4 textbook.